Hi everybody, welcome back to Gov 2001. We ended the last session by focusing on models as abstractions, and I gave you a silly little stick figure of a human and I asked you whether that was real, and that of course didn't make sense. We came to understand that a model is an abstraction. It is either useful or not useful. It's not necessarily the correct thing. It's just useful or not useful. But so we need to design it to be useful. One incredibly useful set of models are statistical models. They may seem more abstract than models of people that are stick figures, but that's not actually true. It's not remotely true. A model of a cloud, well, however you design it, is going to differ massively from the clouds up there. A model of a person, as we talked about, no matter what your model is going to differ massively from actual human beings because of the differences across human beings mean that any model is never going to reflect all of the features of them. So what we need to do is design our statistical models for the things that we care about. And why we're developing them now is for inference, for taking facts we have to learn about facts we don't have. So we're going to design these models to try to identify the quantity of interest, make it, it's going to be very precise. So therefore we're also going to identify and model the data generation process from which we get the data. Then that's going to help us figure out how the data that we don't have, the facts that we don't have, are going to be related if the data generation process is the same to the facts that we actually do have. So that's what we're going to focus on. So let's get started. So here's our outline that we're doing, at least at the moment. It's not the outline of the whole class, of course. We did overview and logistics. Today we're going to do statistical models and also data generation processes. Okay. Let's see. So let's go back here. And I think we're all ready. So statistical models. Let's begin with some notation. Again, we have to be very precise. So our dependent variable, or our outcome variable, sometimes called, we're going to label it as y. Y is going to be a vector. It's going to be n for n observations. It's going to be n by one vector. Think of it as a column, right? Columns hold up buildings, rows go like this. So it's going to be a vector or a matrix of one column. Little y of I is going to be one of the numbers in a column. It's going to be a number after we know it, and capital Y of I is going to be a random variable before we know it. So think about what we're talking about here. The idea is that when we set up the design for our analysis, we're going to have y sub 1, and y sub 1 is going to be generated by some data generation process, or the one that we specify. And if we ran the experiment, or the analysis, or the survey, or the random draw from a population, or whatever it is, that first observation could be different each time. The number that it is now in this particular experiment is this little y of I. That's what we see in our data set. But what we're going to focus on is the data generation process, the process from which we get the data that we actually observe. And in that, that little y sub I isn't necessarily going to be the same thing in every data set. In fact, it's going to vary. It's going to vary randomly. That's what we're going to imagine. It's going to vary randomly, and so that's what the big Y is. Okay, so the little y is our data set. The big Y is the variance or the variation in the little y across data sets. Okay, so that's a key difference. It's very commonly misunderstood. Therefore, a dependent variable can be a column of numbers in your data set where there's variation across it, or it could be the random variable that is represented for each observation in the data set. So the first number in your data set or the 12th number in your data set doesn't vary, it's just one number, but conceptualized as across data sets, it actually varies. Okay, that's the dependent variable. We're also going to have explanatory variables, also called covariates, or independent variables, or exogenous variables. These have different connotations. Covariates means that they covary with the dependent variable. Independent means somehow they're not a function of the dependent variable, they're independent. Of course, they're not going to be independent of each other typically, and they're not independent of the dependent variable because they're going to be related to the dependent variable, but they're independent of the dependent variable causing it. And exogenous is an explicit reference to the idea that the explanatory variables might or might not cause the dependent variable, but they are exogenous. They cannot be affected by the outcome variable. Okay. These variables are going to be described in our setup as X. So X is going to be a big matrix of rows. So there's n rows. Think of it as a survey data set where each row is a person, and k columns. Each column might be the answers to it, might be a survey question, and each cell is person 12 and variable gender, and the answer is male or female or something else. The way we have it set up here is that the big matrix X is n by k. This notation with little braces and a little x sub ij in there, that notation refers to, right on the right-hand side here, this notation refers to one element within the big X. And the ij is the ith row and the jth column. So there's n by, so the matrix is n by k, but that's just one number. So that way we can use either notation if we like. And just to give you a little bit more, we can think of X as a set of columns where little x1 is the column for the first variable and little xk is the column for the kth variable. We can also think of it as a set of rows. So row I goes from xi1 through xik, right? They all have I, and the thing that varies there are the variables. So that's a way of describing the row. X, in the way that we're going to model this, at least at first and most of the time, is that X is going to be fixed. It's not going to be random. It's going to be fixed across our draws of our data sets. That may not be true, and we may need to change the model to pay attention to that, right? It could be fixed if we decide that some people are going to get the medicine and some people are going to get the placebo when we decide who gets what. Perhaps we're going to randomly assign people to the medicine and the placebo. And the outcome, how well people do on the medicine, is going to be not decided by us. It's going to just be a random variable that's going to be part of the experiment. But in every single experiment, in every single data set, even if we only collect one data set, but across data sets, the x's may be fixed. We may often imagine race or gender or certain demographics to be fixed variables. At the moment, we're going to imagine all the explanatory variables are fixed, so they're not random. The randomness here is in the outcome variable. That will change, but that's what we're going to focus on. Okay, so let's take that notation and let's go to regression. Okay, so first of all, there's standard regression notation, which I think you should have seen. Y of I is a linear function of some explanatory variables. X sub I beta is matrix notation for beta 0 plus beta 1x1 plus beta 2x2 plus beta 3x3 dot dot dot, as many as you like. This notation describes what's going on for observation I. See, there's I there, and I there. And X sub I beta is a scalar, right? It's one number. And Y of I is one number, and epsilon's one number. On the right-hand side here, we have X beta, which we think of as the systematic component, the part that we're sort of seeking. It's the pattern. It's the thing that persists despite the randomness. And epsilon is the randomness. It's the stochastic component. We then describe the stochastic component. The stochastic component is epsilon. Epsilon may actually be in regression notation normal. It's on average 0. That's the first element there. But it varies, and the variance of epsilon sub I is sigma squared. So this is a standard homoscedastic, which means constant variance, so that sigma squared has no subscript. So it's a linear normal homoscedastic regression. So it's standard notation. Okay, now I'm going to change this to an alternative notation. The advantage of alternative notation in this case is that we're going to be able to massively generalize it. Okay, so it's not only going to be linear regression, linear normal regression, but it's going to be any type of analysis, a vast array of analyses, not any type of analysis, but quite a lot of analyses. Okay, so this is also going to have two equations, but we're just going to represent the same information, exactly the same information in a different way. So we're going to have y of I being normal, but now, so it's y as normal. So it recognizes that y is stochastic, right? Because up here, y is stochastic because it's got the epsilon. Over here, y is stochastic because it has, the whole thing is drawn from a normal distribution. Now, up here, this is drawn from a normal distribution too because epsilon is the normal distribution. Over here, I'm just recognizing that y of I has a mean of mu I. And it has the same variance. Well, what's mu I? Mu I is the mean. Well, what is the mean? Well, it's x beta, right? It's the same x beta as over here, okay? So I'm just calling it out and I'm labeling it. So this x beta is now mu, okay? And it actually identifies it. So all we've done here is here we have the systematic component plus the stochastic component, and the second equation identifies what the stochastic component is. And in the alternative notation, we have the stochastic component as the first line, and the systematic component is the second line. Okay, one isn't more important than the other. At the moment, since we haven't generalized this, these are exactly the same. I mean, their representations. The representations are different, and you may prefer one versus the other. I'm going to hope that you're going to prefer the second in a minute because it turns out to be much easier to generalize the alternative notation than the standard notation. Okay, so we're going to focus on that. All right, so let's understand the alternative regression notation. By the way, go back here. You might want to write that down. Right, we're going to use this. But if you don't want to write that down, I'm going to show you an alternative way to think about it. That's even more general. And so here's the alternative regression notation. I want you to conceptualize what this is. Let's think about it, and then we'll go back and before we generalize it completely, let's ask ourselves a question. Make sure that we really understand it. Okay. So. What I have here for every line in this thing, every line is one distribution. So this is mu1, and this little distribution from which the observed realization yi is drawn, and that's the yi. And here's a different one where mu I is different. And here's a third one where mu I is different. Note, each of these is normal, although freehand drawn by Gary. The variance of each of these is exactly the same. That's the homoscedastic part. That's the sigma squared that remains fixed. But the mean is differing. How do the means differ in regression? They differ because mu of I is equal to xi beta. So the means are linearly related. That's the key thing that's going on here. The means are linearly related, but these things are varying. Okay, now you can think of this in the standard notation, but I want you to think about this in this alternative notation, where first y is drawn from a normal distribution with mean mu defined or driven by the x's here, but from the same normal distribution aside from the mean shift. Okay, now to convince yourself that you understand this alternative notation, to convince yourself that this alternative notation is the same as the previous notation, I want you to answer this question. Okay, so here's just a little quiz. Okay, is a histogram of y your outcome variable for if in a regression? Is it a good test of the normality of your data? So you take the data, you take your dependent variable, a column of n observations, and you plot them in, you sort them into bins, and you plot the height of the bins, right? And you get a little distribution. Is that actually a good test of normality? In other words, if that looks sort of normal, do you say to yourself, yeah, y is normal, it fits this assumption. And if it's massively bimodal or it's skewed or it's in other ways not normal, then we would conclude that the assumption that we made on the previous page was wrong. Okay. So is a histogram of y a test of normality? Feel free to hit pause, think about this. You're much more likely to learn and get something from this if you commit yourself to an answer. And if it's wrong, that's okay. You'll figure it out. So I'm pausing here for you while you think about it. Okay. So what's the answer? The answer, whoops, let's go back here. The answer is that it is not a good test of normality. It's not a good test of normality. The reason why is because y is driven by a normal distribution, but it's also driven by the means that differ, right? So these means differ. So let's follow a good way to answer most methodological questions. In fact, this is probably the best strategy to think about the answers to methodological questions. First of all, what is the simplest possible case that simplifies the most you can, but no more than you can, right? So you don't want to simplify beyond where all the features of the problem are gone. But I'm going to take the simplest possible case. So how about a regression with one explanatory variable, and that explanatory variable is dichotomous, so let's say it's gender, and we have some continuous dependent variable. Okay. Now suppose the coefficient on gender is big, so gender is a big effect. There's a big difference between men and women on whatever the outcome variable is, okay? And the data were generated by a normal distribution. So epsilon, or E, and epsilon would be normal. Y is distributed as mean mu, comma sigma squared. The sigma squared is the same thing for everything. The mu is very different for the men and for the women, right? Maybe the men are here, the women are here. And the sigma, let's say, is small for each. So we have a little distribution for the men and a little distribution for the women. So that means if we plot the y's, we're going to get bimodality. So y is bimodal, but conditional upon x, that is after you adjust for the x, the two distributions come together and you'll see one little distribution. So a histogram of y alone, not paying attention to x, that was the mistake, is not a good measure of normality. Okay, I just asked you that question just to see whether we understand it. I'd go back, make sure you convince yourselves that you understand that problem. Okay, now let me generalize this alternative notation to basically most statistical models. Okay, or a very large number of statistical models. Okay, so for starters, we're going to have y being distributed in some way according to some probability distribution with two parameters. I'm going to go through each one of these parameters very specifically. That's going to be our stochastic component. And we're going to have a systematic component. G is not linear, right? It could be any kind of functional form. All right, so let's go through each of these things. I'm going to color the slides in unison. Okay, so first of all, y, which colors blue, right? Let's get that cursor out of the way. So y is the random outcome variable. In the model, it's the random outcome variable. We would run the model and get one set of data, and the one set of data is what we would have in our data set. But for starters, the way we're thinking about it is y is the random outcome variable. F is the probability density in regression. That would be normal. But now we open up ourselves to the possibility of a count distribution, a Bernoulli distribution for binary variables, a distribution that could be skewed, a distribution on just the positive numbers that's continuous. It opens up quite a lot of additional possibilities for modeling, and each of which may be incredibly important for your substantive problem. Okay, so that's the probability distribution. Theta, remember that was mu in a regression, but theta is a systematic feature, some systematic feature of the density that varies over I. Okay, so it's a systematic feature, which means we're going to calculate something from that probability distribution. There's a lot of things that you could calculate from a probability distribution. It could be the mean, it could be the variance, it could be the area to the right of 0.5, probability that the Democrats win the election, let's say. It could be the amount of skewness. It could be the amount of kurtosis, how peaked the distribution is. It could be how fat the tails are, whether they're really big and unexpected possible outliers. There's an infinite number of possibilities for that, but it's just some systematic feature of the density that varies over I. We might be interested not only in the mean, which all regression models are basically focused on, we might be interested in the variance. We might be interested in focusing on how much things vary. So we could study, let's say, the mean liberalness of public policies from states, from the US states. And we could try to figure out what explanatory variables predict that, and that would be a pretty interesting study. But alternatively, we could have as our quantity that's varying across the states, not the mean, not the expected point on the liberal to conservative continuum, but the variance of that. Maybe there's some states that always produce a certain type of ideological policy, a point in the ideological policy space. And there's other states that produce answers all over the place. Sometimes they're very conservative, sometimes they're very liberal, sometimes they're in between, and they move all over the place. Wouldn't it be a really interesting study to try to figure out which states do that and which states basically are always predictable? Right? That's a different question than I think has been asked before. At least I don't know of an example where that particular question has been asked. But as I think about the model, those kinds of substantive possibilities open themselves up to us. And those are the kinds of things that we need to think about. So theta sub I can be lots of different things. Alpha is going to be some parameter. We're going to call it an ancillary parameter is the technical term. And the main thing is it's just some feature of the probability density that, doesn't vary over I. So in regression, theta I is mu sub I, and alpha is sigma. So it's homoscedastic, doesn't have a subscript. So that's the only real distinction between the two. G is the functional form. In regression, obviously, it's linear. So we're making a linearity assumption. Well, the world isn't always linear. It may not even usually be linear. The reason we do and focus on linearity is because, frankly, it's easier. It's easier mathematically. That's why most of our models are linear. It also magically works in amazing ways as a reasonable approximation, but that doesn't mean that you should be assuming linearity, and you should not ever be constrained by your models. You should not be constrained by your computer programs. You should not be constrained by the methods that happen to be available. You should be able to focus on the substance and get the methods out of the way. Allowing G to be linear or non-linear in some interesting way will be something that will free you in those ways. And then we're going to have x sub I as an explanatory variable vector for I, and we'll have beta as the effect parameters. So g of x sub I sub beta in the regression model is just x sub I times beta, but there's lots of other ways of putting those together. So this is the generalized alternative notation. For most models, we're going to keep revisiting this. We're always going to ask what is the stochastic component for this model and what is the systematic component for this model. Those two things is what we need to focus on. Okay. All right. In all these models, there are important forms of uncertainty. Remember, this is our alternative statistical model, our stochastic component and systematic component. Well, this model always has estimation uncertainty. Estimation uncertainty is the lack of knowledge about beta and alpha. Estimation uncertainty comes because of your failing and mine. You're failing because you didn't collect an infinite amount of data. You didn't collect all the data that was available. You sampled data. You collected data only based on what was available. If we could collect all the data in the world, we wouldn't have any uncertainty of estimation because we would have it all, okay? So that estimation uncertainty is reflected in the fact that we don't know alpha and beta. Now let's just look closely. We also don't know theta, but theta, of course, is perfectly determined by x, which we know, and beta, which I just said we don't have knowledge of. So the only thing we really need knowledge of here is alpha and beta, right? Because g is going to be assumed, f is going to be assumed, theta is going to be determined by the right-hand side here, and y is going to be a function of everything else. So if estimation uncertainty is beta and alpha, and in fact, as n gets larger, it goes away, and you can see that, in fact. If you do things the right way, you get standard errors or confidence intervals, uncertainty estimates of beta and of your estimate of beta and alpha, and those standard errors or confidence intervals will get smaller and smaller, or should get smaller and smaller as n gets larger. Okay, where are we here? All right. So that's estimation uncertainty. Fundamental uncertainty is the stochastic component, and it's basically completely represented in F. So F is the distribution. Fundamental uncertainty is represented by the stochastic component. It exists no matter what you do, or no matter how many observations you collect. It's a function of the world. There's also model dependence. So there's uncertainty about the whole setup, right? Because we assumed F, and we assumed G, and we assumed alpha, and we assumed theta, and we assumed beta. We assumed the whole thing. Well, suppose the whole specification's wrong, or some part of it's wrong, and it may make everything wrong. We will eventually focus on model dependence. I want to keep reminding you of that, so as not to take these models too seriously. But for now, we're going to ignore the model dependence because we first have to learn how to model, how to estimate, and then we'll get to model dependence. So here's the quiz, okay, to make sure you understand this slide. If you know the model, that is, you know the model exactly, and you know alpha and beta exactly, is r squared 1? Okay, so you know the rules, right? So commit yourself to an answer. I'm not going to ask you in front of everybody. The goal is not to humiliate anybody. The goal is for you to understand what you understand and what you don't understand, okay? And that way you'll wind up understanding everything, okay? So if you know the model and you know alpha and beta, is r squared always going to be 1, okay? Is the fit of the dots to the regression, right? So we have x and we have y, and we have a bunch of dots, and we have a line. If you know the model, the data generation process exactly, is r squared 1? Do all the dots fall exactly on the line? What do you think? Okay, the answer is no. And the reason why it's no is because there's still a stochastic component. This stochastic component is still incredibly important, right? Even if you know alpha and beta, if you know beta, then you know theta, okay? Because we already know x. So we know theta, and I'm stipulating that we know alpha. So we know alpha and we know theta. Now, let's follow the rule that I gave you earlier. Let's take the simplest possible case. I don't know what the simplest case is, but let's take one that we all think we understand, which is normality. So if you have a normal distribution here with mean 4 and variance 12, and you take random draws from that, do they follow any known pattern? Yes, because they follow a normal distribution. Are we able to predict them exactly? No, no way, right? Because there's still stochastic variability, right? So even if you know the data generation process and you have no estimation uncertainty, all you get to know is the model of the world. Now this is really good. It's good that r squared is not 1. It's good that you can't predict everything exactly, because that's actually the way the world works. In the real world, we don't actually get to be able to, we can't actually predict everything exactly. So this makes perfect sense. That means we have a model that includes the uncertainty due to our failings, and it includes the uncertainty due to the fact that the world produces different results every time. It is true that if we ran the election again, exactly the same result wouldn't be the case. You might decide you're going to vote for the other candidate, right? Well, maybe not this time, but maybe next time, right? There might be a traffic accident and some people wouldn't make it to the polls. All kinds of things that we choose not to code into our explanatory variables as fixed known features of the system. wind up being in the stochastic component. And so it's really important when you have a model to include a stochastic piece of the model. Okay. So now let's make these more specific so that we can go on and develop them in more detail and use them in our research. So first some systematic components. There's a linear one, there's an exponential one, there's a logistic one. Here, let's look at these. Okay, so the blue one on the left is, I can give you this nice thing, isn't that cool? I like to play with these toys. On the left are a bunch of different possible linear relationships. Now, this expression here is just x beta, right? Remember I said x beta is beta 0 plus beta 1 x1 plus beta 2 x2 all the way on up. What's being drawn up here is just 1x and mu. Now, if I had y here, then I'd have to have a bunch of dots. So I'm just putting mu so you can see the patterns. These are the lines. If it were data and we were making predictions of mu, that might be y hat. One other thing is that I have 1x there. I don't have 5 x's because 5 x's we need a hyperdimensional space. Okay, so for 1x, there's 1x on the horizontal axis. There's a mu on the vertical axis, and we can figure out where the line is. Right, it's somewhere in here. Like where is that line? It could be because it could be positively sloping, could be negatively sloping, could be flat, etc. If we have 2 x's, then we're going to have to figure out how to generalize this. Right, so we'll get there. We'll get to figuring out how to think in high dimensional space. But basically, we're going to have an x1 along this axis, an x2 along this axis, and a mu along the vertical axis. And instead of a line, instead of these lines in the graph, we're going to have a whole plane that cuts across this thing. And then in 3 dimensions, or 3 variables, and 4 variables, we'll get there. Okay, but think of the simplest possible case. It's better to understand it. So that's linear. Okay. Here's a logistic function. So the x beta in this expression, which you may never have seen before, and that's totally fine. And if you have seen it before, let's understand it better than you knew it before. The x beta in this expression is the same x beta conceptually as in the linear expression. It's beta 0 plus beta 1 x1 plus beta 2 x2. But as we know, that linear expression can be any number. Right? It can be greater than 0. It can be less than 0. It could be anything. Okay. Suppose instead our theta, our systematic quantity that we care about that varies over the observations, is pi, is a probability. Right. So in this case, it's probability of a 1. Right. We might be predicting the outcome of election. What's the probability that the Republicans will take the Senate? And let's call that pi. And pi is going to vary over the observations, so there's a little subscript on there. So pi is our theta in this case. Now, pi is a probability. Pi can't be 12. It's got to be between 0 and 1 because probabilities are always between 0 and 1. So it doesn't really make sense to use a linear regression if we can use something better, right? So what would be better? Well, better would be something so that no matter what our predictions are, they wind up in what's called the unit interval. The unit interval is just a fancy term for between 0 and 1. Could be 0, could be 1, but somewhere in there. Okay. So how does that work? Well, let's look at this math here. So the math says 1 over 1 plus e to the minus x beta. If you play with that, any number that you stick in for x beta and put a minus sign in front of, and then that e is on your calculator. You put in, you type in a number and you hit e. It's exponentiated. Okay, e is actually a number. It's 2.71, etc. Okay, and it turns out to work. It works very nicely. And no matter what number you put in for x beta, no matter what numbers you put in for x, and no matter what beta gets to be estimated at, no matter what, if you stick it in there, the pi will always be between 0 and 1. Okay. In fact, if these are finite numbers, they will always be between 0 and 1, exclusive of the endpoints. A way to see it is the color-coded graph up here. What this does is it turns the linear relationship from the first one into what we could think of as escalator curves, right? But the escalator could be very steep going one way, or it could be All right, this is one escalator curve, this is an escalator curve with a negative sign, and basically as x is going up, what's happening to that probability? Maybe if we have this one, the probability is increasing, but it's increasing slowly over here, faster in the middle, and then faster up at the top. Or maybe actually it's over here whereas when x is increasing, the probability is decreasing. Or maybe it's only one little piece of this logistic curve. Okay, so that's known as a logit, okay, or a logistic regression. And we'll run logistic regressions. It's very good for voting or survey research. We'll use this kind of thing a lot. Okay, next functional form is an exponential functional form. So suppose our outcome variable is a variance, right? Suppose that quantity, that theta, is not a mean, and it's not a probability. Suppose it's a variance, like the example I gave you about policy, outcomes, and states. Well, a variance can be positive, but it can't be negative, right? It can't be zero, or it could be zero, but it can't be negative. So we need some functional form that always is negative. So we take the same x beta from the linear regression here, and we exponentiate it. That's the same e, 2.71, et cetera. And here's a plot. So if you look at that plot, then x is along the horizontal axis, sigma or sigma squared is on the vertical axis, and no matter what, as x gets larger, then sigma gets larger, no problem, but as x gets smaller, according to this line, then it never hits zero. Same thing if the coefficient is negative, right? It never hits zero. So that's it. That means what we're doing here is we're identifying classes of functional forms, and the statistical method will then pick out one set of betas, which is basically a member of the class of functional forms. Okay, so each is a class of functional forms. Beta is what we might call an effect parameter. Doesn't mean it's a causal effect. We'll have to figure out what that means. It's an effect parameter with a different meaning, right? We're going to set beta, and once we set beta, eventually we will estimate beta. It will pick out one member of the class as the best summary within the class. So if we assume that everything follows a logistic function, that means it's one of these, but we don't know which one. That's done by theory because we know that our outcome of interest is between 0 and 1, and so we choose a logistic function. Not the only function that's between 0 and 1, but one useful one. We use that, and then we use statistics to pick out which one of those curves is going to be the best one. Okay, all right. So let's look at the examples of the systematic components. Standard procedure is for picking these, use theories. Assume a class of functional forms that delineate all essentially remaining possible relationships, because you've eliminated all the relationships that don't fit into that setup. You know, if they're not linear and you've chosen linear regression, then it's not possible to come up with a result that says, hey, it's nonlinear. So that's a really important step. We're going to use theory to choose the class. We're going to use data to estimate the member of the class. We're going to remain uncertain no matter what we do here because of estimation uncertainty. We didn't collect an infinite number of observations. Because of fundamental uncertainty, because the world is fundamentally uncertain and we haven't coded everything up in the x's, and because of model dependence. So all of those three things gives us those uncertainties. If we choose the wrong family of functional forms, what happens? Well, we have specification error and potentially bias. We still get the best linear or logistic or exponential approximation to the correct functional form, so that's pretty good. Okay, here's an example where it could be good and where it might not be good. Let's take the one on the right here. Okay, let's take the one on the right here. So the actual functional form is red between x on the horizontal axis and mu on the vertical axis. And suppose we chose a linear regression. Well, we're not going to get the right answer. It's going to be wrong. But maybe for our purposes, that's pretty close, right? In fact, the uncertainty in estimation of the linear regression is actually may actually be bigger than the difference between the linear regression and the actual functional form. So we might be, well, this might be fine. Maybe this is a great example. Now, what about if we have something like this? Over here, we have a problem. So if the actual relationship between x and mu is very strong, but in this, it's strong, but it's just this particularly weird case. In that case, then the true relationship we miss completely. And the best linear approximation to that actual relationship, the blue approximation to the red, it's still the best linear approximation, but it would convey no relationship when in fact there's actually a very strong relationship. So, so it's very good that we have the best linear logistic whatever approximation, but it's only good if the differences are not very big. So we'll have to pay attention to that. Okay, so that's systematic components. Now let's think about stochastic components, the distributions. So here's some normal distributions. Right, so the normal distribution is continuous and it's unimodal, right? There's only one mode. It's symmetric between the left and the right, and it's unbounded, which means it covers the whole number line. We can switch and look at the log normal distribution. So if you had income, where as you're measuring income, let's say, it could only be a positive number, sometimes the log normal distribution is used to model income. And all these distributions only cover the positive end of the continuum. It wouldn't make sense to use a normal distribution which gives some probability of there being negative outcomes. And if there can't be negative outcomes in the way that we're measuring this, then it doesn't make sense to do the normal. Obviously, people don't understand what it means to be a graduate student with negative income, but let's put that aside. Okay. So log normal is very commonly used in economics to model income, in fact. It's continuous, it's unimodal, it's skewed, right? You see how it's skewed, it's not symmetric, and it's bounded from below by 0. So those are two continuous distributions. Here's a Bernoulli distribution. Bernoulli distribution is discrete. The outcomes are binary. It's just a 0 or 1. Here's 3 different Bernoulli distributions. They can look in different ways. Basically, there's either a 0 or a 1. Those are the only possible outcomes. You either vote or you don't vote. And then there's a probability, and the probability of 1 is high, and the other is going to be low, or the reverse. They sum up to 1. The sum of the two columns is 100%, so it's 1. That may be a good model for certain purposes. Might be good for turnout and not turnout, but it's a model. Every one of these things is a model. That one feels like it could actually be the correct model. But you know, if you say vote and don't vote, well, what if you went to vote, but for whatever reason you didn't pull the lever the right way and your vote wasn't counted? Is that vote, not vote, or is that really a third category? You really have to think about that. You have to model that. It has to be part of your model. You have to decide whether you want to count that. Okay. Here's another example. Speaking of count, if you count things, one possible set of distributions, class of stochastic components, is what's known as the Poisson distribution, named after not that famous fish, but named after a guy named Poisson. The Poisson distribution is a discrete distribution. It's countably infinite on the non-negative integers, which just means it can't be negative, and it can be 0, 1, 2, 3, all the way on up. But it can't be 2.3, and it can't be -4. And that's very useful to count the number of coups d'état or the number of suicides, or the numbers, basically. There's other count distributions. There's other distributions that are symmetric. There are other distributions that are asymmetric. We'll have to pick them out. And I haven't even shown you the mathematical form for these. You may have seen it for the normal and probably not for others, or maybe some for others, that's fine. But we'll get into exactly what the math looks like. At the moment, I want you to have the feel for the fact that all statistical models will have a systematic component, and those systematic components could be linear, nonlinear in various ways, and every statistical model will have a stochastic component, which is the distribution, and the distributions can be of many different types, continuous, discrete, and many different types within continuous and discrete. And these are just some examples in a qualitative sense. Okay. How do you choose them? Well, if one is bounded, so is the other. So if your systematic component is bounded, right, if your systematic component says can't go above 0, then you don't want the stochastic component saying that it can go above 0. If the stochastic component is bounded, say it's bounded between 0 and 1, the systematic component must be globally nonlinear. So what does that mean? That means if the stochastic component says that the outcome variable can always be between 0 and 1, and you're moving x, there isn't any way for it to be linear because unless it's always flat, because if it goes up, if it's going up, eventually when x gets large enough, it's going to make this pi be above 1. And we've just decided it was impossible because it was bounded. So if the stochastic component is bounded, the systematic component can't be linear. It has to be globally nonlinear. Although it might be linear in a specific area, so that maybe we could use the simple methods of linear regression in that area. In fact, actually, when we run models on the democratic proportion of the two-party vote in US congressional elections, the results are pretty much that in almost every election, there's some uncontested seats, which we could treat separately, but if it's a contested election between a Democrat and a Republican, no candidate gets less than 15%. That's not strictly true, but it's pretty close, okay? So in the vast majority of cases, you just don't get near the extremes. And the extremes are the case where if you had x going, being large enough, it might cause the predicted probability to be above 1, or if x were small enough, it might cause the predicted probability to go below 0. And so it's often the case that in analyses of elections, district-level election results, we often use linear regression, knowing that it's definitely the wrong model globally, but it actually works pretty well. After all, the wrong model, what does that mean again, right? It has to be useful. And this made it simpler, but the deviations from what is probably closer to accurate don't really matter, okay? So we'll have to figure out what matters and what's useful. Sorry, those are the same thing. We have to figure out what's useful and matters and what's more likely to be correct and which one we want to choose. So all modeling decisions, we have to remember, are about the data generation process. When you pay attention to a new paper, you pay attention to the chain of evidence from the world to the data in the paper. If you're studying a new subject, it's how the data got there. Pretty much everything determines that. It's the first question you ask of every empirical paper. Okay, now what if you don't know the data generation process? You just sort of came upon some data and you really don't know it. And frankly, we usually don't know it completely. We often know parts of it, but we don't know all of it. Well, the problem then is even more model dependence. So our first approach is going to be to make some reasonable assumptions and check the fit of the model. And we're going to check other observable implications of the assumptions to figure out whether maybe there's a different model that we can use that might fit better, that might be less model dependent. We later on will avoid the model dependence by relaxing assumptions. We can choose more flexible functional forms in certain cases. We can choose more flexible distributions that allow us to choose within them the distribution that's more likely to be right. We're going to develop methods to detect model dependence, to find it in data that we have, and then we're going to be able to have methods that will actually remove some of the model dependence so that we can analyze the data without that problem. And you may have heard of matching for causal inference. That's one example of a method to remove some model dependence from data. Okay. All right. So we are up to data generation processes with simulation. I am going to now talk for a bit about these, and then we will continue. And so let me pause here and we'll click the next video to get right to it. So thanks for joining me, and hang on one second.